Hello students. So today we will see our NCERT chapter 8, which is aldehyde, ketones and carboxylic acid. Today is theory part 2, and the section which we will cover today is from section 8.2 to 8.3. This is the disclaimer. So what is the objective of today's lecture? After attending this lecture, you will be able to understand the topics which we are going to cover today. So today we will see the important methods of preparation of aldehydes and ketones. And we will correlate the physical properties of aldehydes and ketones with their structures. Now for your reference, I have mapped the NCERT sections which we are going to discuss today. So we will discuss section 8.2, which is preparation of aldehydes and ketones. We will see section 8.2.1, which is preparation of aldehydes and ketones, which is the subtopic. Section 8.2.2, which is preparation of aldehydes. Section 8.2.3, which is preparation of ketones. Then we will see section 8.3, which is the physical properties. And lastly, we will summarize whatever we have covered in today's lecture. So let us start with the general methods of preparation of aldehydes and ketones. So preparation of aldehydes and ketones can be done by following method. So there are certain methods by which we can prepare aldehydes and ketones. So first method that we are going to see is oxidation of alcohols. So this process involves converting alcohols into aldehydes or ketones by adding or removing hydrogen. Okay, so this is basically oxidation, that you are oxidizing alcohols to aldehydes or ketones. Second method which we will see is dehydrogenation of alcohols. Now what does the word dehydrogenation means? This method, it involves the removal of hydrogen from alcohols to form aldehydes and ketones. The third method which we will discuss is using hydrocarbons. So we will use hydrocarbons to prepare aldehydes and ketones. Okay, so this method, it involves complex reactions such as ozonolysis or the use of specific catalyst. So one by one we will discuss all of these three methods in detail. Okay, so let's start with the first method, which is oxidation of alcohol. So alcohols can be oxidized to form aldehydes and ketones. So we have to form this oxidation of alcohols, and alcohols can be oxidized to form aldehydes and ketones. So there are certain common oxidizing agents which we use. So to achieve this oxidation, we use oxidizing agents. So what does these oxidizing agents do? So these are the substances that facilitate the removal of hydrogen or the addition of oxygen to the alcohol. So the oxidizing agent which we use is pyridinium chlorochromate, which is called as PCC. Now PCC is particularly useful because it selectively oxidizes primary alcohol to aldehyde without over-oxidizing them to carboxylic acid. So it stops the process at aldehyde without over-oxidizing it to carboxylic acid. Next oxidizing agent which we can use is chromium trioxide, which is CrO3 in anhydrous medium. So this agent is also a powerful agent and it can oxidize the alcohols efficiently. And if I talk about CrO3 also, then it also prevents the over oxidation of alcohol. So that means it oxidizes alcohols to aldehyde without over oxidizing it to carboxylic acid. So primary alcohols yield aldehydes. So when you oxidize primary alcohol, what you get? You get an aldehyde. So if you look at this particular reaction over here, here you see a primary alcohol. Primary alcohol, why? Because the carbon to which your OH group is attached is further connected by one carbon only with this carbon. Okay, so this is a primary alcohol. So when you use an oxidizing agent like PCC or CrO3, you see you get an aldehyde. So this alcohol is oxidized to an aldehyde. So this CHO group over here shows that we have gotten aldehyde. Now let us see with the help of an example. This is a benzyl alcohol. Benzyl alcohol, why? Because the carbon to which your OH group is attached, that carbon is directly attached to a benzene ring. And this is primary benzyl alcohol. Because see, this carbon is further connected by one carbon only. So this is primary benzyl alcohol. And when we use a PCC, so it oxidizes this alcohol to an aldehyde and forms a benzaldehyde. Benzaldehyde, that means to a benzene ring, a aldehyde group is attached. So see, you see over here that it oxidizes alcohol to aldehyde without further oxidizing it to carboxylic acid. And primary alcohol yields aldehyde. Now we will see the secondary alcohol yield ketones. Okay, so secondary alcohols, in this case, they will yield ketones. So if you look at this particular example, you see this is a secondary alcohol because the carbon to which your OH group is attached is further connected by two carbon atoms. So this is a secondary alcohol. When you use a oxidizing agent like CrO3, which is chromium trioxide, you see that it gets oxidized to a ketone. Ketone, why? Because see that this carbonyl group is connected by two carbon atoms. One is this R and one is this R dash. So this R and R dash can be same also or it can be different also. So secondary alcohol get oxidized to ketones. Example, if you see, this is a isopropyl alcohol. So this is a secondary alcohol. How? Because the carbon to which your OH group is attached, that carbon is further connected by two carbons. See, this is CH3 whole twice. So this carbon is further connected to two carbons. So this is a secondary alcohol. And when you use an oxidizing agent like chromium trioxide, you see you get an acetone. And acetone is a ketone. Why? Because to this carbonyl group, you have one methyl group on one side and other methyl group on another side. So this carbon atom is further connected to two methyl groups. So this is an acetone, which is a ketone. So primary alcohol gives aldehyde and secondary alcohol gives ketone. Now, you need to remember that tertiary alcohols do not participate in this reaction. Tertiary alcohols means in which the hydroxyl group is attached to a carbon. That carbon atom is connected to three other carbon atoms. So, there is no hydrogen in this case. Okay. So, tertiary alcohols do not undergo this oxidation reaction, because there is lack of hydrogen atom on the carbon which is attached to the OH group. Okay, because if you see, if there is a tertiary alcohol, the carbon is further connected to three other carbon atoms. So it lacks a hydrogen on the carbon which is attached to the OH group. So this absence, it prevents the necessary structural change for oxidation to occur. Okay, so that is why a tertiary alcohol, because of lack of hydrogen atom, it do not participate in this reaction. So now we have seen the oxidation of alcohols. Now we will see the dehydrogenation of alcohols. Okay, so if you see the word dehydrogenation, what you understand by the word dehydrogenation? It means removal of hydrogen. So conversion of alcohols. So dehydrogenation involves the conversion of alcohols into aldehydes or ketones by the removal of hydrogen atoms. So what happens in this reaction? So alcohol vapors, they are passed over heavy metal catalyst like silver and copper. So these metal, they facilitate the removal of hydrogen, which makes this reaction more efficient. So let's break down this dehydrogenation process. So it involves several steps. Okay, what happens in first step? In first step, there is a formation of carbon oxygen double bond. Okay, so see over here, there is the formation of carbon oxygen double bond. In next step, there is breaking of oxygen hydrogen and carbon hydrogen bonds. Okay, so in addition to formation of carbon double bond oxygen, it involves the breaking of oxygen hydrogen and carbon hydrogen bonds in alcohols. So this bond breaking is essential for removal of hydrogen atoms, which allows the formation of carbonyl group. And last, there is loss of hydrogen molecule, which completes your dehydrogenation process. So if we look over here, as I told you, that in case of dehydrogenation of alcohol, there is breaking of carbon hydrogen bond and oxygen and hydrogen bond. Now, if I explain you this in simple words, then see over here, this carbon hydrogen bond is breaking. That means this carbon is left alone. And here also oxygen hydrogen bond is breaking. That means this hydrogen is left alone. Now both oxygen and carbon friends have left them. Now they will say what to each other? Let's do friendship. So they will make a bond between themselves and you will get a carbon oxygen double bond. Okay, so this is what happens in dehydrogenation of alcohols. Now in this case also primary alcohols give aldehydes. So if you look at this, this is a primary alcohol. The carbon which is connected to OH group is further connected by one carbon atom only. And when you pass it, alcohol vapors, when it is passed over heavy metals like copper and Ag, so it gives you an aldehyde. So this CHO group over here, see, this is an aldehyde over here. So primary alcohols give aldehydes. Now we will see secondary alcohol gives ketone. So secondary alcohols undergo dehydrogenation and they form ketone. If you see, this is a secondary alcohol because this carbon is further connected by two carbon. And when you treat it with copper, you see you get a ketone over here. Now tertiary alcohols undergo dehydration and form alkenes. Now this is in case of tertiary alcohols. Unlike secondary alcohols, the tertiary alcohols, they do not form ketones or aldehyde through dehydrogenation. So tertiary alcohols do not undergo dehydrogenation. Instead, they undergo dehydration. So they undergo dehydration to form alkenes. Okay, so tertiary alcohols, they lack a hydrogen atom on the carbon with the hydroxyl group. Okay, that is why they favor dehydration over dehydrogenation. So dehydration means removal of water and dehydrogenation means removal of H2. So remember students, tertiary alcohol undergo dehydration and they form alkenes, not aldehydes or ketones. Now we will see third method, which is using hydrocarbons. So we have seen the other two methods. Now we will look at third method, which is using hydrocarbons. So preparation of aldehydes and ketones using hydrocarbons involve two methods. So there are two methods by which you can prepare aldehydes and ketones using hydrocarbons. First is ozonolysis of alkenes. So in this process, your alkenes react with ozone to form ozonides, okay, and which are further cleaved to produce aldehydes and ketones. We will see in upcoming slide about this process. Next is hydration of alkynes. So this second method is hydration of alkynes, and this involves adding water to alkynes in the presence of a catalyst to form aldehydes or ketones. So now we will discuss one by one about these processes. First is ozonolysis of alkenes. So what happens in this process? This reaction cleaves the carbon-carbon double bond. So you see this is carbon-carbon double bond. So this cleaves the carbon-carbon double bond into carbonyl compound. That is, I can say that ozone adds to the double bond of alkene and forms an intermediate which is called ozonide. Okay, which is a cyclic structure. So to carry out this process, we need specific reagents. So the primary reagent is ozone, which is O3, which acts as an oxidizing agent. And we also use zinc dust and water to facilitate the reaction. So what happens when you get an intermediate which is called ozonide, it is then treated with zinc dust and water, which further breaks it into aldehyde and ketones. And one more important thing, that zinc, it prevents the further oxidation to carboxylic acids by removing extra oxygen. So it prevents the further oxidation. Now if you look at this process, it will give you a more clear picture. This is an alkene, okay? Now when you treat it with ozone, which is O3, you get an intermediate which is called ozonide, okay? You see that 3 oxygen atoms get attached. Now what happens is that when you treat it with zinc and water, so zinc gets attached with this oxygen, okay? So zinc gets attached with this oxygen and these two bonds cleave from here. Okay, so one is this carbon oxygen bonds get break and one is this carbon oxygen bond. Okay, so what happens to fulfill this valency of carbon now? It forms carbon double bond oxygen because oxygen loves to form double bond. So you get corresponding aldehydes or ketones. Now whether you get aldehyde depends if you get an aldehyde, then one side of carbonyl there will be H, okay, and other side can be R group. And if you are getting ketone, then on both sides there will be R group. Okay, so is this clear? Now I'll give you a simple trick how you can just write your product from the reactant. So if this is an alkene, just break this double bond. If you break this double bond, give one oxygen to each of this carbon. So you get an aldehyde and you get an ketone. Okay, so you get an intermediate which is ozonide, and see at the cursor on the screen, this bonds break from here and this breaks from here. Okay, this breaks from here and this breaks from here. Look at this particular example. This is an alkene. Okay, now when you treat it with ozone, in presence of zinc dust and water, you will get a ketone and an aldehyde. So I tell you a simple trick. If this is alkene, just break this double bond. If you break this double bond, this particular will get one oxygen and this will get one oxygen. So see over here, you're getting a ketone because on both side of carbonyl group you have carbon which is attached, R and R dash group, and this is an aldehyde. Okay, because on one side of carbonyl there is hydrogen atom, other side there is R group which is attached to a carbon atom. So you get ketone and an aldehyde. Example, let us see. If you have a 2-methyl propene, okay, if this is a particular example, when you treat it with O3, that is ozone, in presence of zinc dust and water, you see, just break this double bond. Okay, just break this double bond. So this particular will get one oxygen and this CH2 will get one oxygen. So when this gets one oxygen, this is propane 2 on. Okay, and this is a aldehyde which is methanol. Okay, so this is C double bond O CH2 and this is C double bond O. One side there is methyl and other side also there is methyl. So this is propane 2 on, one ketone and one aldehyde which is methanol. So this is ozonolysis of alkene. So there is one simple trick. Just break this double bond. One oxygen give to this carbon and one oxygen to this carbon. Okay, and you'll get corresponding aldehydes and ketones. Now B part we will look about hydration of alkynes. So alkynes hydration involve addition of water to carbon-carbon triple bond. Okay, so you add a water to carbon-carbon triple bond. Now, to carry out this reaction, you need specific reagents. So, we use sulfuric acid, which is H2SO4, and mercuric sulfate, which is HgSO4. So, these reagents, they are essential as they facilitate the addition of water to alkyne. Now, remember that this hydration of alkyne follow Markovnikov's rule. Now, what according to this rule, the OH group from water attaches to a more substituted carbon. This means it will bond with a carbon which has more carbon atoms attached to it. Okay, and the hydrogen from the water, it will get attached to a less substituted carbon. So this is the carbon with fewer carbon atoms attached. Okay, so if you see, there is addition of water, so there will be addition of OH and hydrogen. So OH gets attached to more substituted carbon and hydrogen gets attached to less substituted carbon. Now the initial product of this reaction is an enol, which is an intermediate. Okay, and this enol then undergoes tautomerization, a process where it rearranges to form a more stable ketone, and the final product is more stable because of the stronger carbon oxygen double bond. So look at this particular example. You have propine, which is an alkyne, because this is triple. There it is triple bond. When you treat it with sulfuric acid and mercuric sulfate, you get an intermediate, which is a enol intermediate. Okay, so if you see over here, water gets attached. Okay, so if you see, water gets OH gets attached to more substituted carbon. So this carbon is more substituted. So OH gets attached to this carbon, and this carbon is less substituted carbon. Okay, so hydrogen gets attached to this carbon, and then further this enol intermediate tautomerize to form more stable ketone. So this is the final product, which is propane 2-on, which is a ketone. So 1, 2, 3, second position denotes where this is a carbonyl group. So this is a ketone which you get as final product. Now, acetylene is the only alkyne that's yield an aldehyde. Okay, so if you see, this is an exception which you need to remember, that acetylene, it is the only alkyne that yields an aldehyde. So instead of yielding an ketone, it yields an aldehyde, which is called, that aldehyde is called acetaldehyde. Okay. Now we will see further preparation of aldehydes. Now the preparation of aldehydes can be done by following three methods. So by these three methods you can do the preparation of aldehydes. First is using acyl chloride. Okay, so acyl chlorides, they are reactive compounds that can be converted into aldehyde through specific reaction. And this reaction is specifically known as Rosenmund reaction. Next is from nitriles and esters. So second method is preparation of aldehydes from nitriles and esters. And third is using hydrocarbons. So one by one we will look at all these three preparation methods. First is using acyl chloride, or we can call it as acid chloride. So we will see that hydrogenation of acyl chloride is carried over PDBaSO4 catalyst. So the first step involves the hydrogenation of acyl chloride using a palladium catalyst which is supported on a barium sulfate, or I can say PDBaSO4. So this catalyst combination is crucial because it facilitates the reduction process more efficiently. Now, barium sulfate plays a key role over here. Why specifically barium sulfate? So barium sulfate, it reduces the activity of palladium catalyst. Now this is important because it helps control the reaction, preventing it from proceeding too quickly or aggressively. Okay, so you need to remember over here that it reduces the activity of palladium, and because it helps control the reaction. So BaSO4 prevents over reduction to alcohols. Now BaSO4, it prevents over oxidation to alcohols, or I can say over reduction to alcohols. Okay, this means that it ensures that the reaction stops at the aldehyde stage, which is our desired product. If you look at this example, this is a reaction of using acyl chloride. So this is benzoyl chloride. Okay, and when you do the hydrogenation, which is carried over palladium BaSO4 catalyst, first is hydrogenation. Okay, hydrogenation, and then this hydrogenation is carried over palladium BaSO4 catalyst, then you get a aldehyde. Okay, so this benzoyl chloride is converted into aldehyde. Now, this reaction is very commonly called as Rosenmund reaction. So, you need to remember this name of Rosenmund reaction. And what is happening in Rosenmund reaction? That there is hydrogenation of acyl chloride, which is carried over palladium BaSO4 catalyst. And the final product which you get is benzaldehyde. Now, we will see second, which is from nitriles and esters. So preparation of aldehydes from nitriles and esters can be done using following reagents. So first is stannous chloride under acidic conditions. So first you can use SnCl2 in presence of HCl. And another you can use diisobutyl aluminum hydride, which is commonly called as Dibal-H. Now, Dibal-H is a selective reducing agent, meaning it can target specific functional groups without affecting others. Okay, so if you have to prepare aldehyde from nitriles and esters, you can use these two reagents. Now, we will see their reaction. First is using SnCl2 in presence of HCl. Now, what happens initially? We have a nitrile where there is triple bond between carbon and nitrogen. So, initially we have a nitrile. Now, this nitrile is treated with SnCl2, which is stannous chloride, in presence of HCl. What happens? As a result of this treatment, we form an intermediate, and that intermediate is called imine intermediate. Imine, where there is double bond between carbon and nitrogen. Okay, so this intermediate is a key step in conversion process. Okay, because it set the stage for the formation of final product. Now what happens? The imine undergoes hydrolysis and it yields the corresponding aldehyde. So if you look at this particular reaction, starting we have a nitrile, that is there is a triple bond between carbon and nitrogen. When you treat it with SnCl2 in presence of HCl, you get an intermediate which is called imine, where there is double bond between carbon and nitrogen. And when you further hydrolyze this imine, you get a corresponding aldehyde. So this is the final product. From nitrile, you are reducing this nitrile to aldehyde using SnCl2 and HCl. So if you look at the particular example, this is ethane nitrile. Okay, there are two carbon atoms and one nitrile group. So this is ethane nitrile. When you treat it in presence of SnCl2 and HCl, you get an intermediate which is imine. And when you further hydrolyze it, you get an aldehyde. So this is ethanol. In aldehyde, the E of alkane is replaced by Al. Since there are two carbon atoms, so this will be ethanol. So this reaction is very famously called as Stephen reaction. So you need to remember the name, that this reaction is called as Stephen reaction. Now we will see another one which is using Dibal-H, or we can call it as diisobutyl aluminum hydride. So nitriles, they are selectively reduced by Dibal-H to imines. Okay, so if we focus on these steps, so Dibal-H over here is a mild reducing agent that allows us to stop the reduction at imine stage rather than reducing it to an amine. Okay, so this is a mild reducing agent. So imines are hydrolyzed to yield corresponding aldehydes. Okay, so once we have our imines, the next step is to hydrolyze them to get the aldehyde. So if you look at this reaction, initially you have a nitrile. When you treat it with diol H, you get an intermediate which is called imine. There is double bond between this carbon and nitrogen. And when you further hydrolyze this imine, you get a corresponding aldehyde. Example, if you see over here, this is hex 4E nitrile. So this is a CN group which is attached. How many carbon atoms if you count? 1, 2, 3, 4, 5, 6. 6 carbon atoms. The root word will be hex. Okay, so hex 4E nitrile because this is double bond. When you treat it with diisobutyl aluminum hydride, first you will get imine as an intermediate, and that imine is then hydrolyzed to yield an aldehyde. And this is hex 4-enol. This is an aldehyde group. If you count again, you have 6 carbon atoms, and on fourth position, this is one double bond. And in case of aldehyde, the E of alkane is replaced by al. So you get hex 4-enol. Okay. Now we are going to see that esters can be reduced to aldehydes using diol H. So diol H or diisobutyl aluminum hydride is a reducing agent that is particularly used for converting esters to aldehyde. Okay. Now if you see, this is an ester. When you treat it with diol H in presence of water, if you see, the temperature over here is 78 degrees Celsius. Okay, when you treat it with water, you get a corresponding aldehyde over here. So if you look at this example, this is an ester. You see, this is an ester group which is called as ethyl and deconate. So esters are named as alkyl alkonate. Okay, so this alkyl part comes from which is attached to this oxygen. So this ethyl is attached to this oxygen. So this is ethyl. And if you see, there are 9, 10, 11 carbon atoms. So this is undeconate. When you treat it with diol H in presence of water, you see you get a corresponding aldehyde, which is undecanal. Because how many carbon atoms are there? 9, 10, 11. 11 carbon atoms are there. So this is undecanal. Now if you see the mechanism of how you transform it to diol H. So first, diol H reduces esters to form tetrahedral intermediate. Okay, so first what happens, that diol H we know is a selective reducing agent. Okay, so it will, diol H, it will attack your ester and it will form a tetrahedral intermediate. So if you look at this, this is an ester. When you treat it with diol H in presence of water, you see that this diol H, it attacks the ester and it forms this tetrahedral intermediate. And at low temperature, this intermediate is stable, and it further on workup, it gives you an aldehyde and an alcohol. Okay, so we are starting with an ester. You treat with diol H, you get an tetrahedral intermediate, okay, which is stable at low temperature, and when you do workup, you get an corresponding alcohol and an aldehyde. Okay, so now let's start from the third method, which is using hydrocarbons. Okay, so we will see the preparation of aldehyde using hydrocarbons. So hydrocarbons are compounds which are made up of hydrogen and carbon atoms. So preparation of aldehydes using hydrocarbon involve 3 methods. So there are 3 methods by which we can prepare the aldehydes. First one is the oxidation of methyl benzene. Now what is the another name of methyl benzene? So methyl benzene is also known as toluene. So what happens in this reaction? Toluene is oxidized to form benzaldehyde. Okay, and here we are specifically targeting the methyl group which is attached to the benzene ring. Next method is side chain chlorination followed by hydrolysis. So this method involves adding chlorine to the side chain of hydrocarbon, which is then converted into an aldehyde through hydrolysis. And the third one method which we will discuss is Getterman-Koch reaction. So it is a technique to produce aldehyde from hydrocarbon. Okay, and this reaction involves carbon monoxide and hydrochloric acid in the presence of a catalyst. So I just gave you an overview about all these three preparation methods. Now one by one we are going to discuss all of these three methods. So first we will talk about oxidation of methyl benzene. So this process involves adding oxygen to methyl benzene and transforming it into an aldehyde. So now this can be done using the following reagents. Okay, so we can do the oxidation of methyl benzene using the following reagents. First one is chromyl chloride, that is CrO2Cl2. So this reagent, what is the nature of this reagent? It is an oxidizing agent, meaning that it helps add oxygen to methyl benzene. B is chromic acid. Chromic acid is CrO3. So like chromyl chloride, chromic oxide is also an oxidizing agent. So it helps convert methyl benzene into an aldehyde by facilitating the addition of oxygen. So these are the two reagents that you can use for the oxidation of methyl benzene. So first one we will study is now use of chromyl chloride, that is CrO2Cl2. Now CrO2Cl2, it selectively oxidizes the methyl group of an aromatic ring to form an aldehyde. Okay, so it is a powerful oxidizing agent. Let us look at an example. So the oxidation of toluene to benzaldehyde. So toluene is a simple aromatic compound with a methyl group which is attached to a benzene ring. Now by using chromyl chloride, we can convert this methyl group into an aldehyde group. So this happens in two steps. In step number 1, the methyl group of toluene, it is oxidized to a corresponding chromium complex. Okay, so the methyl group of toluene is oxidized to form a chromium complex. Now look at this particular reaction. This is toluene. Okay, that is to this benzene ring a CH3 group is attached. When you use chromyl chloride, that is CrO2Cl2, in the presence of CS2 over here, okay, which is a non-polar solvent. So what is the use of this CS2 over here? So it dissolves chromyl chloride and the organic substrate, okay, which facilitate the formation of an intermediate. So since CS2, it is a non-reactive, so it does not interfere with the reaction and it allows us the desired oxidation. Okay, so when you treat toluene with CrO2Cl2 in presence of a non-polar medium which is CS2, you get a chromium complex. So that is the methyl group of this toluene, it is oxidized to a corresponding chromium complex. So this is a chromium complex which you get. Now step number 2 is we hydrolyze this chromium complex. So hydrolysis, what do we mean by hydrolysis? So hydrolysis is a reaction with water that breaks down the complex. So using water you break down a complex, that is hydrolysis. So when you will hydrolyze this chromium complex, you will ultimately yield benzaldehyde. So if you look at this reaction, this is a chromium complex. When you hydrolyze this chromium complex, you get your final product which is a benzaldehyde, which is an aldehyde. So you see to this benzene group, an aldehyde group is attached. So this is a benzaldehyde. Now this reaction is family called as Itard reaction. Okay, so it is named after a chemist who discovered it. And it is a classic method for preparing aromatic aldehyde. So aromatic aldehyde which is a benzaldehyde. So you need to remember this name, that this reaction is called Itard reaction. Next we will see by use of chromic oxide which is CrO3. So it is also a common oxidizing agent. Now, CrO3 is a powerful oxidizing agent. Okay. Now, if I say it is an oxidizing agent, then I hope you all know that oxidizing agent are substances that can accept electrons from other molecules, causing those molecules to become oxidized. Okay. So, you should all know these basic terms. So, under what happens when you are using CrO3, that is chromic oxide, under mild anhydrous condition, it can specifically oxidize the methyl group which is attached to the aromatic ring, and finally it would convert it into an aldehyde group. Okay, now this is a controlled reaction. Now, what do I mean if I say controlled reaction? That means it prevents the over oxidation, okay, which is important in maintaining the desired products. So it controls the over oxidation. Example, let us look at this example, that toluene, which is a common solvent and a starting material, so it can be oxidized to benzaldehyde in two steps. So first step is you are treating toluene with CrO3 in acetic anhydride. So when you will treat toluene with CrO3 in acetic anhydride, so this reaction will yield benzylidene diacetate. Okay. Now if you see over here, acetic anhydride, it acts as a solvent. So it helps in acetylation process. That means it is an addition of an acetyl group to a molecule. So if you see over this image, you will see that this is a toluene. When you treat it with CrO3 in acetic anhydride, this forms benzylidene diacetate. Okay. So that means you are adding the acetyl group to the molecule. And step 2 involves hydrolyzing this benzylidene diacetate to yield benzaldehyde. So water helps us to remove the acetyl group, which gives us the final product, which is benzaldehyde. So if you'll see, you will do the hydrolysis, then this water breaks down the compound using, in hydrolysis, you break down compound using water. Okay, so you will see that final product which you get over here is benzaldehyde. Now we will see second one, which says side chain chlorination followed by hydrolysis. So aromatic aldehyde, they can be prepared through side chain chlorination of alkyl benzene. Okay, so this process involves adding chlorine to the side chain of an aromatic compound. So if you see example, then toluene, which is a simple aromatic compound, it can be converted into benzaldehyde by side chain chlorination. And this transformation involves two-step process. First step is that toluene, it is converted to benzyl chloride. So when you treat, when toluene, it is treated with chlorine gas in the presence of light, so this reaction converts toluene into benzyl chloride. So if you see over here, this is toluene, okay, and when you treat it with chlorine gas, which is Cl2 in presence of light, so this toluene gets converts into benzyl chloride. Okay, that is to this benzene, CHCl2 group is attached. Now what happens in step 2? In step 2, the benzyl chloride is hydrolyzed to produce benzaldehyde. And you will see the reaction, this is benzyl chloride, and when you hydrolyze it in the presence of temperature, which is 373 Kelvin, finally you will get the product, which is benzaldehyde. So this was using side chain chlorination. Now this method is commonly used to produce benzaldehyde. So this method is not just a lab experiment, it is used commercially. To produce benzaldehyde. Now if I talk about benzaldehyde, then it is an important compound which is used in fragrance and flavor industries. Okay, much like vanilla extract, which is used in baking. Now we will see third one, which is Getterman Koch reaction. So this is a useful method for synthesizing benzaldehyde. So what happens in this reaction? We start with benzene or a substituted benzene. Okay, and then we treat it with carbon monoxide, which is CO, and hydrochloric acid. So what is the nature of this gas, which is carbon monoxide? It is a colorless and a odorless gas. Whereas if I talk about HCl, which is hydrochloric acid, then it is a strong acid which is commonly used in labs. So the product of this reaction is benzaldehyde or substituted benzaldehyde. So for this reaction to occur, we need a Lewis acid catalyst. So a catalyst is required in this reaction. Okay, what is the use of a catalyst? So catalyst basically speeds up your chemical reaction without getting consumed. So we will see that what common Lewis acid which we can use in this Getterman-Koch reaction. So first one which we can use is anhydrous aluminum chloride, that is AlCl3. Okay, so these compounds being a Lewis acid, they facilitate the reaction by accepting electron pairs. Okay, so Lewis acid, if I say what is their nature, being electron deficient, they accept the electron pairs. Another Lewis acid which you can use is cuprous chloride, that is CuCl. Now let us see with an example. So starting, you are taking in benzene. When you are treating it benzene with carbon monoxide and HCl in presence of a Lewis acid catalyst, which can be anhydrous AlCl3 or cuprous chloride. So you get the final product, which is benzaldehyde. That is, to this benzene, a aldehyde group is attached. Now we will see the mechanism of this Getterman-Koch reaction. So we will see stepwise mechanism. So first step is formyl chloride equilibrium. So that means this compound is in equilibrium, means it can easily switch between different forms. Okay, so if you see over here, you have carbon monoxide. When you treat it with HCl, so carbon has a negative charge and oxygen has a positive charge because it is forming 3 bonds. Now carbon being negatively charged will attract this H positive of HCl. Okay, so it will form this, and then chlorine has left from here. The chlorine, okay, it can attack on this carbon and you can form formyl chloride. So this is formyl chloride equilibrium. Step number 2 is formation of formyl cation. So this is a positively charged ion. So this step is essential for attaching the formyl group to the aromatic ring. So if I talk about formyl cation, it is highly reactive. That means it can easily interact with the molecules. If I talked in context of Getterman's reaction, then the reactivity of this formyl group, then the reactivity allows the formyl group to attach to the aromatic ring, which forms an aldehyde. So if you see over here, here we have formyl chloride and here you have AlCl3, which is a Lewis acid catalyst. Okay, so chlorine, it can donate its lone pair to this Lewis acid catalyst because it has vacant empty orbital. So what will happen now? So this AlCl3 gets attached and this oxygen lone pair will come here and this will leave from here. So you will get a formyl cation plus AlCl4 minus. Now step 3. If I talk about, it is an electrophilic aromatic substitution. Okay, so in this process, the aromatic ring, so this is the aromatic ring, it acts like a magnet for a positively charged electrophile. And in this case, what will be your electrophile? It is a formyl cation in this case. This is your electrophile. So as the reaction will progress, the formyl cation, it attaches to the aromatic ring. So see over here with the pi electrons, it will attack on this carbon. So your formyl cation will attach to this aromatic ring, forming an intermediate complex. Now, finally, this intermediate complex undergoes deprotonation. That means it loses a hydrogen. So, you'll see over here that AlCl4 will abstract this hydrogen from here, and this bond will go down from here. So, it loses a hydrogen ion and it forms a final product, which is the aldehyde product. Okay, so this was the Gettermann's Koch reaction. Now we will see the preparation of ketones. So in this we will know that ketones, they are characterized by a carbonyl group which is C double bond O, which is bonded to two carbon atoms. So preparation of ketones can be done by the following three methods. First is using acyl chlorides. So acyl chlorides, they react with organometallic compounds like Grignard reagents to form ketones. So this reaction is a nucleophilic acyl substitution where the Grignard reagent attacks the carbonyl carbon and replaces the chloride. Next one is from nitriles. So nitriles, they can be converted into ketones through a reaction with Grignard reagent, which is followed by hydrolysis. So this process involves breaking the triple bond and forming a new carbon oxygen double bond, because in nitriles there is C triple bond N. And next is using benzene or substituted benzene. So it happens by a process which is called as Friedel-Crafts acylation. So this involves reacting benzene with an acyl chloride in the presence of a catalyst like aluminum chloride. So first we will start with acyl chloride. Now one by one we will discuss all these three methods. So this reaction involves dialkyl cadmium, a compound which we can make from Grignard reagent and cadmium chloride. So you can see over here that acyl chlorides, they react with dialkyl cadmium to yield ketones. Now dialkyl cadmium is prepared from Grignard reagent and cadmium chloride. So when you react Grignard reagent and cadmium chloride, you get dialkyl cadmium. Now the reactions which are involved, so you will see in this reaction you have two molecules of Grignard reagent. This is RMGX. So you have two molecules of Grignard reagent, and when you react it with cadmium chloride, it forms dialkyl cadmium. So this is a type of an organometallic reaction where the organic group is bonded to a metal. So cadmium is a metal and the organic group get bonded to a metal. And you will see you will get a byproduct which is magnesium chloride. Okay, so this is a salt which can be removed from the reaction mixture. Next, we have the reaction between the acyl chloride. So this is acyl chloride and this is dialkyl cadmium. So this reaction produces ketone. So ketone, you will see there is C double bond O, which is a carbonyl group, and both sides it is bonded to carbon atoms, or I can say to alkyl groups. So this cadmium chloride, and you will see over here this CdCl2 or this cadmium chloride which is formed here, it can be recycled or disposed of safely. Why? Because this cadmium chloride, this cadmium compounds, they are toxic in nature. Now let us see with the help of an example. So this is methyl magnesium bromide, which is a Grignard reagent. So see CH3MgBr, which is a Grignard reagent. It reacts with cadmium chloride and it forms dimethyl cadmium. So to this cadmium, two methyl groups get attached. So this is dimethyl cadmium. And in next step, you will see that dimethyl cadmium, which is this CH3 whole twice 2CD, it reacts with propanoyl chloride. Okay, and it forms butane 2-on, and this is what? This is a ketone. To this carbonyl group, one side this ethyl group is attached and one side this methyl group is attached. So finally from propanoyl chloride, when you react it with dimethyl cadmium, you get butane 2-on. Okay, so this is also known as methyl ethyl ketone. And at last you get CdCl2. So as I told you, these compounds are toxic, so proper safety measures are required when you are working with such type of compounds. Now the second method which we will see is from nitriles. So when nitriles react with Grignard reagent, they form an intermediate, and that intermediate is called as ketamine. Okay, so ketamine is the intermediate which is formed. Now the ketamine intermediate, it undergoes hydrolysis. Hydrolysis, it breaks down the intermediate, resulting in the formation of a ketone. So finally you get your product as a ketone. Now look at this reaction. This is a nitrile which is R C triple bond N. When you treat this nitrile with a Grignard reagent, that is RMgX, you get an intermediate which is called as ketamine. So this is the intermediate, that is C triple bond N, and both sides this is one R group, both sides there is alkyl group. And when you hydrolyze it, and hydrolysis, this intermediate, that is ketamine, yields the final product which is ketone. Now let us understand it with an example. So here you see over here you have a nitrile group, that is propionitrile. When you react it with phenyl magnesium bromide in the presence of ether, you get this intermediate, okay, and this intermediate is called ketamine. And when you further hydrolyze it, you get a final product which is propiophenone, or you can also call it as 1-phenyl propanone. So this is finally a ketone. So this is how from nitriles, using Grignard reagent and then following hydrolysis, you get a final product which is ketone. Now third, we will see using benzene or substituted benzene. So this involves a reaction where a benzene, it is treated with acid chloride. So benzene or substituted benzene, it is combined with acid chloride in the presence of a Lewis acid. So a Lewis acid is a compound that can accept an electron pair. Okay. So the final product which you get is a ketone. So the commonly used Lewis acid is anhydrous AlCl3. So you can use a Lewis acid as AlCl3, which is aluminum chloride. Now this compound is crucial because it activates the acid chloride, making it more reactive. So the activation of this acid chloride, it generates a highly reactive psyllium ion. Okay, and this ion is what reacts with the benzene to form the ketone. So if you see over here, this is a benzene, and when you react it with acyl chloride in presence of anhydrous AlCl3, so this AlCl3 activates the acyl chloride, which makes it more reactive. Now the activation of this acyl chloride, it generates a highly reactive psyllium ion. Now that psyllium ion finally reacts with the benzene and it forms a ketone. So finally you get ketone as your final product. Now let us see the stepwise mechanism. So first step is formation of psyllium ion. So this ion is a positively charged species. So you will see when you react acyl chloride with AlCl3, so what happens is that this Cl gets attached to AlCl3, and further you get a psyllium ion. That is, this lone pairs of oxygen come down. At this, it makes a carbon triple bond oxygen, and this leaves from here. So finally you get a psyllium ion, and this is a positively charged species. Next is electrophilic aromatic substitution. So in this reaction, the psyllium ion acts as an electrophile. So it interacts with the benzene ring, which is rich in electrons, because electrophile is electron loving. So it interacts with the benzene, which is rich in electrons. So during this substitution process, the benzene ring, it temporarily loses its aromaticity, which is stable because it is electron rich structure. However, it quickly regains the stability after the reaction. So if you look over here, this is a benzene when you react, and this is a psyllium ion. So this acts as an electrophile, and benzene gives its electron to this electrophile. And finally you get this intermediate, and after that there is this loss of this hydrogen, and then finally you get a ketone. Okay, so if you'll see during the substitution process, this loses its aromaticity, and however it will quickly regain its aromaticity as your reaction will further proceed. So this AlCl4 minus will abstract this hydrogen, and finally you will get a ketone. Now we will talk about the physical properties of aldehydes and ketones. So first we will talk about the physical state. So aldehydes and ketones, they can exist in different physical state depending upon their molecular size. So the lower members, which have up to 4 carbon atoms, they are typically volatile liquid or gases. That means it can easily evaporate and are often found in air around us. Next, if I talk about higher members with more carbon atoms, then these compounds tend to be liquids or solids. And this change in state is because of their increased molecular weight. And increased molecular weight affects that how your molecules interact with each other. So lower members are volatile liquid or gases, and higher members are liquids or solids. Next, if I talk about order of these compounds, the lower members of aldehydes and ketone, they have a sharp pungent smell. This is why some of them, they are used in industrial applications as solvents or in cleaning products. And as the molecular weight increases, the odor of these compounds become less pungent and more fragrant. So that is why some higher aldehydes and ketones, they are used in perfumes and flavorings. Next, further moving on to the physical property, we will talk about boiling point. So aldehydes and ketones, they have boiling point that increases with their molecular weight. Why? Because as the molecular weight increases, the boiling point rises, because large molecules have a more surface area, and if they have a more surface area, it will lead to a stronger intermolecular forces. That is why there is increase in molecular weight. And compared to the non-polar compound like hydrocarbons and ethers, the aldehydes and ketones, they have a higher boiling points. This is because of the dipole-dipole interactions which is present in aldehydes and ketones, and which are absent in non-polar compounds. Because in aldehydes and ketone, there is carbonyl group. So because of the presence of that dipole-dipole interactions, and this interaction is absent in non-polar compounds. However, if I talk about aldehydes and ketones, they have lower boiling points than alcohols of similar mass. Why? Because alcohol, they can form hydrogen bonds, and these hydrogen bonds, they are much stronger than the dipole-dipole interactions in aldehydes and ketones. So the reason is given because of the absence of intermolecular hydrogen bonding in aldehydes and ketones. So that is why they have a lower boiling point compared to alcohols. Because hydrogen bonding, it significantly increases the energy which is required to change the state from liquid to gas. That is why the alcohols boil at higher temperatures. Now look at this particular table. This shows the increasing order of boiling point. So if you go from N-butane to propanol, this shows a increasing order of boiling points with the molecular masses of 58 and 60. So let's talk about the physical properties. So then we will talk about the solubility. So these compounds, first we will talk about their solubility in water. So the lower members, they are soluble because of the hydrogen bonding with water molecules. So if I talk of the lower members of aldehydes and ketones, they are soluble in water. Why? Because they can form hydrogen bonds with water. However, as the hydrocarbon chain increases, the solubility in water decreases. Now, why this happens? This is because the non-polar nature of the longer hydrocarbon chains. So, these hydrocarbon chains, they are non-polar in nature. So, being non-polar in nature, they do not interact well with water. So, that is why their solubility in water decreases. If you look at this particular diagram, then here you have a ketone, okay, and see it can form hydrogen bonding with water, okay. So oxygen being more electronegative over here has a negative charge, and hydrogen has a positive charge. So lower members, they are soluble because of this hydrogen bonding with water molecules. Now, if I talk about the solubility in organic solvents, then they are soluble in most of the organic solvent because of their polar carbonyl group which is present, C double bond O. Now, this allows them to form a strong dipole-dipole interaction with polar or non-polar functional group which is present. Next, if I talk about the polarity, then high polar because of the presence of CO group. Then these aldehydes and ketones, they are highly polar. Why? Because of the presence of C double bond O group. So thank you student for attending this lecture. I hope the concepts which we have discussed are clear. I hope you all have a good day. Thank you.